All right, here we go with the last video for the chapter, and we're going to talk about quantum numbers. Okay, and what I have here is an image from the internet from Mark Winter, who is a professor of chemistry at the University of Sheffield. I want to make sure that I give credit where credit's due because this is a great image. So what we have here is on the far left side, you see in the blue and the gray, those are all s orbitals. Okay, S's are simple spheres, all right? That one S1 at the top left there, and these are all sort of sliced in half. But an s orbital is just a simple sphere, okay? And we have on the left-hand side numbers going down, so 1, 2 through 7. So 1s1, or a 1s orbital, is just a simple sphere, nothing about it. Then if we go down a row, 2s, the 2s is the gray, but the 1s is still there in the center. Okay, so it starts to layer itself as we get larger and larger. So 3, 4, 5, we just keep adding layers. So as we go up in number, we're not forgetting about everything that sort of came before, we're just building on top of things. Okay, so all of those are the s orbitals, this simple spheres, okay, and they become layered like onions. And then if we cross over to the yellow and white ones, those are all p orbitals. And if we look at the p orbitals in row 2, that's this group right here, we see that they're basically like sort of like dumbbells, right? And they go in 3 dimensions, right? So they go in the xy plane, the yz plane, and the left to right, up to down, forward and back, put it that way. Okay, and so there are 3 possible orientations for a p orbital, all right? So 3 separate orbitals, and they all go in a different 3-dimensional direction. And then as we go down, as we get, from 2p to 3p, when we look at 3p, you can see there's that little tiny 2p in the center there, right? And then the 3p is on the outside, and we keep, again, building and building and building as we go down, right? And then the d orbitals, there are 5 possible versions or orientations for a d orbital. Those are the red and white ones in the middle. Okay, so we need 5 ways to describe a d orbital, right? And then the f orbitals are the green and white ones down at the bottom, and there are 7 possible versions of f orbitals. Okay, so quantum numbers, what they are is basically an address. Okay, or a descriptor. All right, it's a set of numbers that describe what is the energy level of the orbital, how big is the orbital, what shape is the orbital, and what orientation is the orbital. Okay, so for the purposes of this chapter, we have 3 quantum numbers. In our next chapter, we will add a 4th quantum number. Okay, so let's get into sort of the nitty-gritties of that. The first number that you'll come across is the principal quantum number. And we've already been dealing with that quantum number. And that's our n value. Okay, we've been talking about n values, doing all kinds of calculations with n values. And so n is our principal quantum number. And if we're looking at our diagram here, that's these numbers right here, right? The 1 through 7 are the principal quantum numbers. And that describes the size and the energy of the orbital, okay? So the n number, we're going to call it the shell number. Okay, so if we look back at our diagram, if I say n equals 2, then I'm talking about 2 shells, or n equals 3, there's 3 shells, okay? And that can be any whole number. N equals 1, 2, 3, etc., up to 7. They theorize that there are more than 7. Mathematically, they can show that more than 7 exist. But as far as our periodic table, 7's the limit. So until we start making or discovering more new elements, 7's where it's at. Okay, so the principal quantum number tells us relative size and energy of a particular shell. Okay, the next one is the angular momentum number. Okay, and what the angular momentum number tells us is orbital shape. right? So the angular momentum number is given as cursive L. And L can be 0, 1, 2, to any number up to n minus 1. Okay, and this will be what we refer to as the subshell number. Subshell. Right, so if I say an L value, I'm talking about the shape of an orbital. Is it a sphere? Is it a dumbbell? Is it a flower? Is it, whatever. Okay, and so the way that goes is for L equals 0, that's an s orbital. Okay, so I can have, going back to our diagram, if S has an L value of 0, I can have a 1, 0, a 2, 0, a 3, 0, a 4, 0, 5, 0, 6, 0, 7, 0, right? Because L of 0 describes an s orbital. So I can have a 5s, I would say 5, 0. Okay? L equals 1 is a p orbital. L equals 2, that's a d orbital. L equals 3, that's an f orbital. Okay, and like I said, maximum value of L is n minus 1. Okay, so you can never have the same value of n and L. N cannot equal L. Right, and our third quantum number is called the magnetic number. Okay, and that's m sub L. Right, and m sub L can be anything negative L to positive L, including 0. Right, and the magnetic number is our orientation number. Okay, so our m sub L tells us, are we talking about a p orbital that's coming forward and back, left to right, or up and down? Right, so for example, if L equals 1, possible values of m sub L will be negative 1, 0, and 1. Right, now let's think about this a little bit. L equals 1, that's a p orbital. And remember we said there were 3 possible orientations for a p orbital? Okay, so the negative 1 tells us one orientation, the 0 tells us another orientation, and the positive 1 tells us a third orientation. So if L equals 2, then m sub L can be negative 2, negative 1, 0, 1, or 2. L equals 2, that's a d orbital. And if we come back to our diagram, let's take a look. So how many orientations do we have for a d orbital? There are 5 of them. Right, so if I have a d orbital, 5 possible orientations, guess what? There are 5 digits for m sub L, so 5 orientations. Okay, so the way this works is we put quantum numbers together, separating them by commas. So if I said 2, 1, 0, okay, that means that I have a principal quantum number of 2. The 1 tells me that's a p orbital. And the 0 tells me that it's a particular orientation. Right, so 2, 1, 0, that's a 2p orbital. And we're we're not going to take you into, does the 0 mean that it's in the x direction or the y direction or the z direction? Suffice to say that only one orbital has that set of numbers. All right, so I could also talk about a p orbital. I could say 2, 1, 1, or 2, 1, negative 1. Okay, these are all p orbitals. And I know that. I know it's a p orbital because of the L value of 1. Right? Now, each individual orbital can hold a maximum of 2 electrons. Okay, so the p orbitals, so I have 3 p orbitals, right? There's a px, a py, and a pz. That means that I can hold a total of 6 electrons. Right? There's 1 s orbital. There's only one orientation for s orbitals because it's just a sphere. So a total of 2. Right? There are 5 d orbitals. Total of 10. And for f orbitals, there's 7. So I'll hold a total of 14 electrons. All right, and we'll get more into how the electrons sort of fit into the orbitals and how things are arranged with the periodic table. It's all wonderfully organized. All right, so suffice to say that with our quantum numbers, our 3 quantum numbers, we get our principal quantum number that tells us how big and how much energy there is in the orbital. We have our orbital shape number, that's our L value. The angular momentum number, that tells us the shape of the orbital. 0 for S, 1 for P, 2 for D, 3 for F. Okay? And then the last one is our orientation number that tells us which direction, which of those, for example, p orbitals are we talking about? All right, so to sum up our quantum numbers, so let's switch colors. So for s orbitals, we have an L value of 0. That means we have an m sub L can only be 0. Okay, which is why we only have 1 s orbital per subshell. Right, p orbitals, we have an L value of 1, so m sub L, -1, 0, or 1. So 3 p orbitals per subshell. Right, d orbitals, we have an L value of 2, so m sub L can be -2, -1, 0, 1, or 2. Okay, these are all possible values of m sub L, given an L value of 2. So 5 orbitals per subshell. And lastly, f orbitals. We have an L value of 3. So m sub L possible values, -3, -2, -1, 0, 1, 2, and 3. So 7 orbitals per subshell. Okay, so for example, if I had an n value of 2, what are the possible values for L and m sub L? Okay, so n equals 2, then I can say L could be 0 or 1. Okay, as long as I am at n minus 1 is the maximum value that L can be. Okay, that means, so if I'm at 0, m sub L just equals 0. If I'm at L equals 1, then m sub L can be -1, 0, and 1. Okay, so these all sort of interact and intertwine as far as what the actual values end up being. It's a lot of what are the possible values. And then if you're given an actual set of quantum numbers, if I said 3, 2, and -3 as your quantum number set, then we have a 3D orbital. Okay, because L value of 2, that's a D. Right, so one of the common questions that you'll see on many types of assignments and exams is a particular set of numbers an allowed set of quantum numbers? So if I gave you quantum numbers of 1, 1, 1, is it allowed? And the answer is no, because n cannot equal L. In order for this to be allowed, I could have it as 1, 0, 0. That would work. Okay, so that's going to do it for our chapter. On our next chapter, we're going to pick up with pretty much right where we're leaving off here and start talking about electron configurations.